Hello, beautiful people. Today, I have prepared the most boring facts about our space imaginable, and we are going through the whole thing from the very first moment anything existed all the way through to how everything eventually ends. And I am gonna take you through it slowly and calmly to help you relax tonight. This took a while to make, so I hope you enjoy it. Also, if you want to listen to these episodes on Spotify, you can go subscribe to my Patreon. There are multiple other benefits and it helps support the channel. But without further ado, let's start at the very beginning. About 13.8 billion years ago, everything that exists was packed into a space smaller than a single subatomic particle. Every atom in your body, every photon of light, every galaxy, every black hole, all of it sitting in a region that occupied essentially no space at all by any measure we would use today. And then it started expanding. Most people hear the words Big Bang and picture a fireball spreading out through some pre-existing darkness. That picture is wrong in a really specific way, and understanding why changes how the whole story feels. There was no pre-existing darkness. There was no empty space waiting for the universe to expand into. Space itself did not exist yet. Time itself did not exist yet. What the Big Bang actually was is space and time beginning to exist and then stretching outward, carrying everything along with it. The universe did not expand into anything. It was everything, and everything simply got bigger. In the first tiny fraction of a second, meaning a decimal point, followed by roughly 32 zeros and then a 1, the universe went through a phase that physicists call inflation. During inflation, space expanded at a rate that makes every other expansion in history look like it was standing perfectly still. In roughly 1/10,000th of a trillionth of a trillionth of a second, the universe grew by a factor of something like 10 to the power of 26. The universe expanded by more than a trillion times its original size before most of a single second had passed. And then inflation stopped. The specific energy field driving that expansion ran out, and the brakes came on entirely by themselves, with no outside cause. All that energy had to go somewhere, and it got converted into a hot and incredibly dense soup of particles and radiation. This soup was so dense and so hot that light could not even travel through it. Particles of light would barely get going before hitting something else and bouncing off in a new direction. The universe in those first moments was completely opaque, more like a thick fog than an empty sky. Between roughly 1 second and about 20 minutes after the Big Bang, the universe was in a very specific temperature window, hot enough for nuclear fusion, but cool enough for the resulting nuclei to stick together rather than immediately getting blasted apart again. During this window, which scientists call Big Bang nucleosynthesis, the protons and neutrons filling the universe began combining. 2 protons and 2 neutrons fused into helium nuclei. A small fraction formed deuterium, which is a heavier version of hydrogen with 1 extra neutron. A tiny amount of lithium was made, and then the temperature dropped below the threshold and the window closed permanently. The recipe was locked in at that point. Roughly 3/4 of the universe's ordinary matter would be hydrogen, about 1/4 helium, and trace amounts of lithium, with essentially nothing heavier than that. Every heavier element, every atom of carbon, oxygen, nitrogen, iron, gold, anything on the periodic table past lithium would have to wait for stars to build it through fusion over billions of years. The universe, at 20 minutes old, had the raw ingredients for fuel, but the complex chemistry that eventually makes planets and people was still an unimaginable distance away in time. The dense, opaque, extremely hot state of the early universe continued for about 380,000 years. That sounds like a long time, but in the context of a universe that has been around for 13.8 billion years, it is really just the very first thin layer of pages in an enormous book. During those 380,000 years, the universe was cooling down, not slowly at first, because when you expand something rapidly, it cools. But even as it cooled, it was still so hot that protons and electrons could not hold on to each other. Every time a proton tried to grab an electron and form a hydrogen atom, the ambient temperature was still high enough to knock it loose again. Atoms could not form. The whole universe was a plasma, a roiling fog of charged particles and light, all tangled up together. Around 380,000 years in, the temperature dropped to about 3,000 degrees. And at that temperature, electrons finally had enough room to settle down next to protons and stay there. Hydrogen atoms formed pretty much everywhere in the universe, all at once. It happened over a span of a few thousand years, and when it did, something changed immediately. The universe became transparent. Before that moment, light could not travel any meaningful distance because it kept colliding with free electrons and scattering in random directions. But once those electrons got locked into atoms, they stopped being obstacles. Light could suddenly travel in straight lines across enormous distances. All the lights that had been trapped in the fog, a vast ancient flash of photons from the moment the universe first became transparent, streamed out in all directions at once. That light never really went anywhere after that. It just kept traveling through an expanding universe, getting stretched and cooled by the expansion over billions of years. By the time it reaches us today, it has been stretched so far down the electromagnetic spectrum that it is microwave radiation, sitting at just 2.7 degrees above absolute zero. Astronomers call this the cosmic microwave background, and it fills the entire sky, coming from every direction equally. It is the oldest light that can possibly exist. A faint cold and perfectly uniform glow left over from the universe's very first clear moment. In 1964, two engineers at Bell Labs in New Jersey, named Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna to pick up very faint radio signals from galaxies. They kept getting a persistent background hiss that was coming from every direction in the sky equally. They could not explain it. They checked all their equipment. They found pigeons nesting in the antenna and cleaned out the nest. They checked again. The hiss was still there, equal in every direction, consistent day and night, completely uniform across the whole sky. They eventually realized they were picking up the oldest light in the universe, and for this they shared the Nobel Prize in Physics in 1978. What this ancient microwave light tells us goes far beyond just confirming the Big Bang happened. The tiny temperature variations in it, differences of about 100,000th of a degree from one patch of sky to the next, are the seeds of literally everything that came after. Those small lumps and ripples in the early universe's density eventually grew under the pull of gravity into the galaxies, galaxy clusters, and the vast cosmic web of filaments and voids that makes up the large-scale structure of the universe today. The whole architecture of the cosmos was written into those almost imperceptible temperature variations in the afterglow of the Big Bang, like a blueprint printed on the oldest piece of paper in existence. After the universe became transparent, it entered a period astronomers call the cosmic dark ages. The name is accurate. With atoms formed and the first light now free to travel, the universe was dark. There were no stars yet. There were no galaxies. There was just hydrogen and helium gas, spread almost uniformly throughout an expanding and cooling dark universe. Not dark the way a room is dark when you turn off the light, but dark in the way a space with absolutely no light sources is dark, where nothing emits so much as a single photon of visible wavelength. The cosmic background radiation was still there, but it had already cooled past the point of being visible light. The universe was genuinely and completely dark. For roughly 200 million years, nothing of note happened at all. Gas drifted, the universe expanded, the temperature kept dropping. That was the entirety of what was going on, but that gas was not perfectly uniform. The tiny ripples in density from the early universe meant that some regions had very slightly more gas than others, differences of just a fraction of a percent, and gravity is patient. Over hundreds of millions of years, gravity slowly pulled that gas together. Regions that were even fractionally denser than their surroundings began to attract more gas, which made them denser, which attracted even more gas. Very slowly, enormous filaments of matter began to thread themselves across the universe like the foam patterns you see on the surface of a calm ocean. Where these filaments intersected, matter piled up into dense nodes. These nodes would eventually become the galaxy clusters we see today. The voids between the filaments emptied out even further. This process of gravity slowly gathering gas over hundreds of millions of years is the engine behind everything that came after. Stars, planets, life, all of it flows from that one quiet fact. Dense places attract more mass than sparse places, so dense places get denser. The universe had no choice but to organize itself. The very first stars formed somewhere around 150 to 200 million years after the Big Bang. These were not stars like our sun. They were enormous, sometimes hundreds of times more massive than anything that forms today, because they were made entirely of hydrogen and helium, since those were the only elements that existed yet. Stars that massive burn through their fuel at extraordinary rates, where a star like our sun will last about 10 billion years on its current phase. These first generation stars may have lasted only a million years or so before exhausting their fuel and exploding. Those explosions seeded the universe with the first heavy elements. When a massive star explodes as a supernova, the energy of the blast forges and scatters atoms heavier than hydrogen and helium in all directions. Carbon, oxygen, nitrogen, iron, silicon. The dust and gas from those first dying stars mixed into the surrounding clouds of hydrogen. The next generation of stars formed from that slightly enriched mixture. When those stars died, they added more heavy elements to the galaxy's chemical budget. Each generation made the galaxy incrementally more complex, slowly building up the raw materials that rocky planets require, and eventually, for chemistry sophisticated enough to build living things. This brings us to how stars actually work, which is one of the more quietly satisfying things in all of physics to sit with. A star begins as a molecular cloud, which is a vast cloud of gas and dust. These clouds are enormous, sometimes spanning hundreds of light years and containing enough mass to build millions of stars. They are also extremely cold, sitting at just a few degrees above absolute zero. So cold that simple organic molecules like methanol can form on the surfaces of dust grains inside them. For millions of years, these clouds just drift through the galaxy, doing essentially nothing. Then something disturbs them. A nearby supernova explosion sends out a pressure wave, or two clouds collide, or the gravitational forces inside the cloud start to win over the turbulence that was holding it spread out. Parts of the cloud begin to collapse inward. As a region collapses, it heats up because when you compress any gas, it gets hot, just like the air in a bicycle pump gets warm when you push the plunger down. Over tens of thousands of years, this collapsing ball of gas heats toward its center while simultaneously flattening into a disk shape, because any rotation in the original cloud gets amplified as the cloud shrinks. The same way a spinning ice skater speeds up when they pull their arms in toward their body. At the center of that disk, the collapsing gas eventually reaches temperatures of around 10 million degrees. At that temperature, something clicks. Hydrogen atoms are being pushed together fast enough and hard enough that they fuse. Two hydrogen nuclei come together to form helium, releasing a burst of energy in the process. This is nuclear fusion, and it is what makes a star a star. The moment fusion ignites in the core, the outward pressure of all that released energy pushing outward exactly balances the inward pull of gravity. The star settles into a stable equilibrium. The leftover disk of gas and dust around the new star is where the planets will eventually form. It is worth slowing down on what the fusion process actually looks like inside the sun, because it is easy to say the word and move past it without really taking in what is happening. In the core of the sun, about 600 million tons of hydrogen are being converted into helium every single second. Two protons approach each other at enormous speeds, driven by the temperature and pressure deep in the core. Quantum tunneling allows them to get close enough to overcome their mutual electromagnetic repulsion, which exists because protons are both positively charged, and like charges push each other away. When they get close enough, the strong nuclear force grabs them and holds them together. One of the protons converts to a neutron through a process called beta decay, emitting a positron and a neutrino in the process. You now have a deuterium nucleus, which is one proton and one neutron. That nucleus then collides with another proton to form helium-3, which has two protons and one neutron. Two helium-3 nuclei then collide to form ordinary helium, which has two protons and two neutrons, releasing two protons back into the mix to continue the chain. The energy released at each step is tiny by human standards, but the sun is running 600 million tons of hydrogen through this process every second, and it has been doing so for 4.6 billion years. The total power output of the sun is about 380 trillion watts, essentially all of it generated in the innermost quarter of the sun's volume. The energy produced in the core takes thousands of years to make its way to the surface, bouncing around in a slow random walk through a layer called the radiative zone, before eventually reaching the convective layer, which carries it up to the photosphere and out into space. The light that left the sun's surface just over 8 minutes ago, the light warming your face on a sunny day, was generated in the solar core thousands of years ago. For a star like our sun, this process continues for about 10 billion years. 10 billion years of the same thing. Hydrogen goes in at the center, helium comes out, energy radiates from the surface, and the star just sits there being a star for an amount of time so vast it is almost genuinely difficult to connect to any human experience of duration. Our sun has been doing this for about 4.6 billion years and has approximately 5 billion more years to go before it runs out of hydrogen in its core. During all of that remaining time, the most interesting thing that will happen to it from the outside is a very slow brightening. The sun gets about 10% brighter every billion years as helium gradually builds up in its core and slightly changes the pressure balance. That is it, 10% per billion years. The most boring stellar story possible. Meanwhile, that disk of gas and dust around the new star has its own story unfolding. When the new star ignites, it blows a lot of the lighter gas out of the inner part of the disk. What is left in the inner disk is mostly rocky material, silicates, metal oxides, carbon compounds. This stuff collides, sticks together, and builds up. Grains of dust become pebbles, pebbles become boulders, boulders become something called planetesimals, which are maybe a kilometer across and start to have enough gravity to pull in more material on their own. Over millions of years, the larger planetesimals dominate because they grow faster than the smaller ones, and the process eventually produces a small number of rocky planets in the inner part of the disk. In the outer disk, where the temperature was low enough for water to stay frozen, the planetesimals that formed had ice mixed into them. Some of these grew large enough to pull in huge amounts of hydrogen and helium gas from the disk before it dissipated, becoming gas giants. Jupiter, the largest planet in our solar system, is essentially a planetesimal that got massive enough to vacuum up an enormous amount of the disk's gas before the sun's solar wind blew the rest of the disk away. Some of the more interesting characteristics of the planets we ended up with came directly from the chaos of that early period. Venus rotates backward compared to most planets, and its day is actually longer than its year, probably because of a large impact that spun it the wrong way early on. Uranus is tilted sideways, with its rotational axis nearly in the plane of the solar system, almost certainly also from a large early collision. Mars has a noticeably thin atmosphere, partly because its smaller size meant it could not maintain a strong enough magnetic field to protect its atmosphere from being stripped away by the solar wind over billions of years. Every quirk of every planet in our solar system is essentially a scar from the violent process that formed it. Saturn's rings are almost certainly a recent feature, cosmically speaking. They are composed of billions of chunks of water ice ranging from dust grain size up to roughly 10 meters across. Astronomers estimate the rings are probably only a few 100 million years old at most, perhaps considerably less, because ice in Saturn's radiation environment gets contaminated with dark material over time, and the rings are still fairly bright and reflective. Something happened relatively recently in geological terms. Either a moon drifted too close to Saturn and was torn apart by tidal forces, or two icy bodies collided, and what is left is spread into that thin, broad, beautiful disk. The Earth itself is the product of at least two major mergers during this chaotic early period. The last of them, the one that formed the Moon, happened about 4.5 billion years ago when a Mars-sized body called Theia collided with the early Earth. The impact was oblique rather than head-on. The debris from the collision was ejected into orbit around Earth, where it gradually came together into the Moon over tens of millions of years. The Moon is, in part, made of material that was once inside the early Earth. Every time you glance up at it, you are looking at something that used to be part of the same body as the ground you're standing on. The solar system that resulted from all of this is, by almost any measure, mostly empty space. People know this in an abstract way, but it is worth taking a moment to actually sit with the scale of it. The Sun is about 1.4 million kilometers across. That is enormous on a human scale. More than 100 Earths lined up in a row would fit across its diameter. But the nearest planet, Mercury, orbits at about 57 million kilometers away. That is roughly 41 sun diameters of empty space between the surface of the Sun and Mercury's orbit, mostly vacuum, with a very thin scattering of charged particles from the solar wind. Venus orbits at about 108 million kilometers, then Earth at about 150 million kilometers, then Mars, then a belt of asteroids, then Jupiter at about 778 million kilometers, which means the distance from the Earth to Jupiter is roughly 5 times the distance from the Earth to the Sunday. Then Saturn, then Uranus, then Neptune, the outermost major planet, at about 4.5 billion kilometers from the Sunday. If you shrank the Sun to the size of a grain of sand, Neptune's orbit would be a circle about 2 meters in diameter, and you would be looking for the grain of sand somewhere near the center of that circle, with essentially nothing else in between. And that is not even close to the edge of the Sun's gravitational influence. A diffuse shell of icy bodies called the Oort cloud circles the solar system at a vast distance and is the source of long-period comets that occasionally fall inward toward the Sunday. The Oort cloud extends perhaps a quarter of the way to the nearest star. We have never directly observed a single object in it. We have only inferred its existence from the comets that fall in from that direction, their orbits pointing back to that distant reservoir. Those comets, when they do fall inward, can take tens of thousands of years to complete a single orbit. They are essentially pristine samples of the material the solar system was built from, frozen at the outer edge of the Sun's influence for billions of years. When they pass close enough to the Sun, heat vaporizes their ice and dust, creating the bright tail visible from Earth. The tail always points away from the Sun, regardless of which direction the comet is traveling, because it is pushed by the solar wind and radiation pressure, not by the comet's motion through space. Jupiter's enormous gravity plays a surprisingly important role in the solar system's long-term stability. Its mass is great enough to perturb the orbits of comets and asteroids, sometimes flinging them out of the solar system entirely, sometimes redirecting them inward. Astronomers have long argued about whether Jupiter acts mainly as a protective shield for the inner solar system by ejecting potential impactors, or whether it also acts as a gravitational slingshot that occasionally sends more dangerous objects toward Earth. The evidence at the moment suggests it is a mix of both, and that the specific architecture of our solar system is neither unusually dangerous nor unusually safe by planetary system standards. The nearest star to our Sun is called Proxima Centauri, at about 4.2 light-years away. 1 light-year is about 9.5 trillion kilometers, so Proxima Centauri is roughly 40 trillion kilometers from us. Going back to that grain of sand model, the nearest grain of sand neighbor star would be sitting about 2.5 kilometers away from our grain of sand sun, with essentially nothing between them. This is the structure of the galaxy, not a dense city of stars packed closely together, but a very thin scattering of points, separated by almost inconceivable distances, all of it mostly vacuum. The stars in the Milky Way are so far apart from each other on average that if you picked a random location inside the galaxy, the probability of it being inside a star would be roughly equivalent to the probability of a randomly placed grain of sand landing inside another grain of sand on a beach that covers all of Europe. Before moving on to the galaxy's larger structure, it is worth spending a moment with what happens to the massive stars that do not end their lives quietly as white dwarfs, because the objects they leave behind are some of the strangest things the universe produces. When a star around 8 to 20 times the mass of the Sun exhausts its nuclear fuel, the core collapses in less than a second. The inner core has been building up iron over millions of years, iron being the endpoint of stellar fusion and the one element that you cannot extract energy from by fusing it into something heavier. Without fusion energy pushing outward, the core simply stops being supported and falls under gravity. In a fraction of a second, a core the size of Earth collapses to a sphere roughly 20 kilometers across. The density becomes so extreme that protons and electrons are forced together to form neutrons. The outer layers of the star, still falling inward, hit this newly formed object and bounce back in a shock wave that blows the rest of the star apart. This is a supernova. The energy released in those 10 seconds is roughly more than the Sun will produce over its entire 10 billion year lifetime, and most of it goes out as neutrinos, so tiny they pass through everything. What is left behind is a neutron star, a sphere about 20 to 30 kilometers across, containing around 1 to 2 times the mass of the Sun. The density is so extreme that a single teaspoon of neutron star material would weigh about 10 billion kilograms. It is a body of matter at the absolute limit of what matter can be without collapsing into a black hole. It spins rapidly, sometimes hundreds of times per second, and it is threaded with magnetic fields hundreds of billions of times stronger than anything we can produce on Earth. Many neutron stars emit beams of radio waves from their magnetic poles. When those beams sweep past Earth like a lighthouse beam, we detect them as extremely regular pulses, sometimes 1,000 of them per second, with a timing precision that rivals atomic clocks. These are called pulsars. The first one was discovered in 1967 by a doctoral student named Jocelyn Bell Burnell and her supervisor, Anthony Hewish. The signal was so regular and so artificial seeming that for a short time the researchers labeled it with an internal nickname meaning little green men, because they could not immediately rule out that something intelligent was producing it. It turned out to be a rotating neutron star, but the story of that brief period of genuine uncertainty is one of the more charming moments in modern astronomy. Two pulsars orbiting each other were used in the 1970s and 80s by Russell Hulse and Joseph Taylor to provide the first indirect evidence for gravitational waves, which are ripples in the fabric of space-time that Einstein predicted in 1916. The orbit of the pulsar pair was slowly shrinking at exactly the rate predicted by Einstein's equations for energy being lost to gravitational radiation. Hulse and Taylor won the Nobel Prize in 1993 for this direct detection of gravitational waves. Themselves had to wait until 2015 when an observatory called the Laser Interferometer Gravitational Wave Observatory, which uses two tunnels each 4 kilometers long and measures the stretching and squeezing of space to a precision of 1/10,000th the diameter of a proton, detected the gravitational wave signal from two black holes merging about 1 billion light years away. There is also the question of how we know how far away any of this is. The universe does not come labeled with distances, and figuring out that a fuzzy smudge of light in the sky is 2 million light years away rather than 2,000 light years away requires a chain of methods that each build on the one before, which astronomers call the cosmic distance ladder. The first rung of the ladder is parallax, which is the apparent shift of nearby stars against more distant background stars as Earth moves around the Sun over the course of a year. This method works for stars up to a few thousand light years away. Beyond that, astronomers use a type of pulsating star called a Cepheid variable, which changes in brightness in a regular cycle that is directly related to how intrinsically luminous it is. Measure how fast a Cepheid pulses, and you know how bright it actually is. Compare that to how bright it appears from Earth, and you get the distance. Edwin Hubble used Cepheid variables in the 1920s to show that certain fuzzy objects in the sky were not clouds of gas within the Milky Way, but entirely separate galaxies at enormous distances. One of the most consequential observations in the history of science. Beyond the range of Cepheid variables, astronomers use a type of stellar explosion called a type Ia supernova as a distance marker. These particular explosions all peak at roughly the same intrinsic brightness, which means that by measuring how bright one appears from Earth, you can calculate how far away it is. A persistent disagreement between different methods of measuring the current expansion rate of the universe, which astronomers call the Hubble tension, is one of the most actively discussed open questions in cosmology right now. Two independent approaches give answers that do not quite match, and the gap is large enough that at least one of them must be incomplete in some way that nobody has yet worked out. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars, depending on how carefully you count the dimmer ones. It is shaped roughly like a barred spiral, a central bar of densely packed stars surrounded by four major spiral arms, with our own sun sitting about 2/3 of the way out from the center on a spur of one of those arms called the Orion arm. The galaxy is about 100,000 light years across and about 1,000 light years thick at our position, though it thickens considerably toward the center. The space between the stars inside the galaxy is not completely empty, even though it is extremely close to being so. The interstellar medium, which is the term for all the gas and dust between the stars, has an average density of about 1 atom per cubic centimeter. Compare that to the air you are breathing right now, which contains roughly 27 billion molecules per cubic centimeter, and you get a sense of how close to empty the interstellar medium really is. But across the enormous distances of the galaxy, even that almost nothing adds up. The total mass of the interstellar medium in the Milky Way is estimated at somewhere around 10 to 15% of the mass of all the stars combined. It is the raw material waiting for the next generation of stars. Though it is being slowly consumed and increasingly difficult to turn into stars as the galaxy ages, the spiral arms of the galaxy are not walls of stars that rotate as solid structures. They are more like slow-moving traffic jams, regions where the density of the interstellar medium and stars is slightly higher than average. Stars drift in and out of them over time. When a star-forming molecular cloud passes through a spiral arm, the extra compression can trigger the cloud to collapse and form new stars. This is part of why the spiral arms appear bright. They are regions where recent star formation has lit up young, hot, blue stars that do not live long enough to drift far from where they were born. Our sun takes about 225 to 250 million years to complete one full orbit around the galactic center. This span is sometimes called a cosmic year or a galactic year. The last time the sun was in roughly its current position in its orbit, the Triassic period was just getting started on Earth, and dinosaurs had not yet appeared. The first time the Sun completed a full orbit after its formation, the universe was less than 5 billion years old. At the center of the Milky Way sits a supermassive black hole with a mass of about 4 million times that of our Sun, called Sagittarius A star. By the standards of galactic black holes, it is fairly average. Some galaxies host black holes with masses of several billion solar masses. Sagittarius A star is quiet at the moment. It does not have a lot of material actively falling into it right now, so it is not producing the enormous jets of radiation that active galactic nuclei produce. It just sits there at the center of everything, bending space-time around itself, while the galaxy wheels around it over hundreds of millions of years. Beyond the Milky Way, the nearest large galaxy is the Andromeda Galaxy, about 2.5 million light-years away. On a very dark night, in a very dark location, you can just barely see it with the naked eye as a faint smudge in the constellation Andromeda. It is the most distant object visible to the unaided human eye, and that faint smudge contains roughly 1 trillion stars. The Milky Way and Andromeda, along with a few dozen smaller galaxies, make up what astronomers call the local group. The local group is part of the Virgo supercluster, which is itself part of an even larger structure called the Laniakea supercluster, a gravitationally connected web of about 100,000 galaxies stretching across 500 million light-years. Laniakea is just one supercluster among many, all threaded through the universe in a vast foam-like network of filaments and voids called the cosmic web. The cosmic web is genuinely one of the most striking things that has come out of modern cosmology. When you map out the positions of galaxies across enormous volumes of the universe, you do not see them spread randomly. You see them arranged in sheets and filaments that look remarkably like the structure of a sponge or a foam, with vast empty voids between them hundreds of millions of light years across. The largest known structure in the observable universe, a wall of galaxies called the Hercules Corona Borealis Great Wall, stretches for roughly 10 billion light years. It is so enormous that light crossing it from one side to the other would take most of the current age of the universe. At this point in the story, two forces are going to determine where everything goes from here. One is gravity, which we have already spent a lot of time with. The other is something far stranger, something we have only known about for a few decades, and which still does not have a satisfying explanation. In the 1990s, two independent teams of astronomers were doing something fairly quiet and technical, measuring the distances to specific stellar explosions in very distant galaxies. These explosions, the same type Ia supernovae mentioned earlier, were being used to map out the expansion history of the universe. By measuring how fast different galaxies at different distances are moving away from us, and comparing that to how far away they are, you can reconstruct whether the universe's expansion has been speeding up, slowing down, or staying roughly constant over time. Both teams expected to confirm that the expansion was slowing down. Gravity pulls matter together, so the universe's expansion, set in motion by the Big Bang, should be gradually losing momentum. What they found instead was that the expansion is not slowing down, it is accelerating. The universe is expanding faster now than it was several billion years ago. This result got both teams the Nobel Prize in Physics in 2011, and it left physicists with a very uncomfortable question. What is pushing everything apart? Whatever it is gets called dark energy, which is an honest admission that the name is mostly a placeholder for something we do not understand. It acts like a property of space itself, meaning that as the universe expands and more space comes into existence, the repulsive effect grows rather than diluting like ordinary matter or radiation would. It makes up about 68% of the total energy content of the universe. It started dominating the universe's dynamics about 5 to 6 billion years ago, when the universe had expanded enough that the density of ordinary matter had thinned out sufficiently for dark energy's constant outward push to overcome gravity's inward pull. What it actually is at a physical level, whether it is the energy of empty space, whether it is some kind of dynamic field, whether our understanding of gravity on cosmic scales is simply wrong, remains one of the most open questions in all of science. There is also dark matter, which is a completely separate mystery from dark energy, despite sharing half the name. About 27% of the universe's total mass and energy is in the form of something that does not interact with light in any way. It does not emit light, does not reflect it, does not absorb it. The only way we know it is through its gravitational effects. The outer parts of galaxies rotate too fast to be explained by the mass of visible stars and gas alone, implying more mass than we can see. Galaxy clusters bend the light from distant background objects more strongly than they should, given only their visible mass. The large-scale structure of the universe, all those filaments and voids, could only have formed the way it did if dark matter provided an invisible gravitational scaffolding for ordinary matter to fall into. Dark matter was present before the first stars, quietly providing the skeleton that the visible universe later filled in, despite decades of experiments designed to detect dark matter particles directly, including detectors placed deep underground to shield them from cosmic ray noise, using thousands of kilograms of purified liquid xenon or germanium crystals, cooled to almost absolute zero. We have never directly detected a single dark matter particle. We have only ever seen its gravity. Together, dark energy and dark matter make up about 95% of everything the universe contains. The ordinary matter, meaning atoms, molecules, everything you can touch and see and smell, every star, every planet, every grain of dust, makes up just about 5% of the universe. We live in a cosmos where the vast majority of what exists is completely invisible to us and understood only in the most indirect terms. Moving on to what we actually use from all of this, because understanding the universe's structure has practical applications that reach into everyday life in surprisingly direct ways. The most immediate example is GPS. The Global Positioning System works by measuring how long signals take to travel between satellites and the receiver in your phone. But the satellites are moving fast at about 14,000 kilometers per hour, and they are operating in a weaker gravitational field than you are on the surface of the Earth. Both of these facts cause time to flow at a different rate for the clocks on those satellites than for clocks on the ground, in different directions and by different amounts, all of which is predicted by Einstein's theories of special and general relativity. The GPS system has to correct for these time differences constantly. If it did not, position errors would accumulate at a rate of about 10 kilometers per day. The precision that lets your phone tell you to turn left in 300 meters depends on engineers applying relativistic corrections derived from the same physics that governs how black holes work and how the universe expands. The study of the cosmic microwave background has given us extremely precise measurements of the basic parameters of the universe: its age, its composition, the geometry of space, and the current rate of expansion. These measurements came from a series of satellite missions, starting with NASA's Cosmic Background Explorer in the late 1980s, then the Wilkinson Microwave Anisotropy Probe in the early 2000s, then the European Space Agency's Planck satellite in the 2010s. Each one mapped the tiny temperature variations in the ancient background light across the whole sky with greater and greater precision. The current best measurements tell us the universe is 13.8 billion years old, to within an uncertainty of less than 1%. That is a remarkable level of precision for a number that large, and it came entirely from studying the faint glow of ancient microwave light. Understanding how stars work has also been directly useful here on Earth. The physics of nuclear fusion in stellar interiors is exactly the process being replicated in experimental fusion reactors. The physics governing how to confine hot plasma in a magnetic field was in large part worked out by studying astrophysical plasmas, including the solar corona, the gas surrounding black holes in accretion disks, and the hot gas that fills the space between galaxies. Space functions as a free physics laboratory where extreme conditions occur naturally, and what we learn from it flows back into engineering on Earth. The study of stellar evolution gave us nucleosynthesis, the understanding of how heavy elements are built inside stars, which tells us where every atom in your body came from. The calcium in your bones was forged in the cores of ancient stars and scattered through space by supernovae. The iron in your blood was almost certainly produced in the final seconds of a dying massive star before it exploded. The hydrogen in every water molecule in your body is primordial, made in the first 3 minutes after the Big Bang. You are a temporary, self-aware collection of stardust. Pulsars also have a practical future beyond just being objects of scientific study. Because their pulses arrive with such remarkable regularity, some to better than 1 microsecond of precision, they function as natural clocks distributed across the galaxy. NASA has been developing a navigation system that uses X-ray pulses from known pulsars to determine the position of a spacecraft anywhere in the solar system or beyond, without needing a signal from Earth. By measuring the precise arrival times of pulses from several pulsars simultaneously and comparing them to known timing models, a spacecraft can triangulate its own location to within a few kilometers, even billions of kilometers from home. It is essentially a galactic GPS built from the corpses of ancient massive stars. Radio astronomy in general gave us something that shapes daily life in a way most people are completely unaware of. The error correction algorithms that underpin wireless data transmission, including Wi-Fi, were partially developed by Australian radio astronomers in the 1990s while working to remove noise from their signals when searching for distant radio sources. The mathematics they worked out to clean up astronomical data turned out to be exactly what was needed for wireless networking in noisy, real-world environments like office buildings and homes. The search for planets orbiting other stars has proceeded so rapidly in the last 30 years that we have gone from knowing of exactly 0 confirmed planets outside our solar system to knowing of more than 5,000 of them. Estimates suggest there are more planets in the Milky Way than there are stars. The main detection method used by NASA's Kepler and more recent planet hunting satellites works by watching for the tiny dip in a star's brightness when a planet passes in front of it. The dip is often less than 1% of the star's total light. From those tiny periodic dips in brightness, astronomers can determine a planet's orbital period, its size relative to its star, and sometimes something about its atmosphere if there is enough light to analyze during the transit. Understanding what those atmospheres contain is one of the central goals of the James Webb Space Telescope, which launched in 2021 and began returning data in 2022. Now let's spend some time with the more speculative side of things. The theories that are grounded in real physics, but that we have not yet been able to directly test. The most established of the theoretical ideas we are still uncertain about is cosmic inflation, which we touched on right at the beginning. The idea that the universe went through an extremely rapid expansion in the very first fraction of a second after the Big Bang explains several things that would otherwise be very puzzling. It explains why the universe looks the same in every direction. If 2 regions of the early universe had never been in contact with each other, how did they end up at the same temperature? Inflation gives them time to reach equilibrium before being rapidly expanded apart from each other. It explains why the geometry of space is flat to such extraordinary precision. Inflation would stretch out any initial curvature, just like inflating a balloon makes a small patch of its surface look flat even though the whole thing is a sphere. And it explains where those tiny density fluctuations that seeded all structure came from, because they were quantum fluctuations in the energy field driving inflation, blown up to cosmological scales by the expansion. The trouble is that we do not know what the field driving inflation actually was. We have no direct observation of it. The search for its fingerprint, a specific pattern of polarization in the cosmic background radiation called B-mode polarization caused by primordial gravitational waves, is one of the central observational goals in cosmology at the moment. Several experiments are attempting to detect it, including instruments at the South Pole, where the cold, dry air makes the atmosphere unusually transparent to microwaves. A more speculative but seriously considered set of ideas concerns what happened before the Big Bang, or whether that question is even meaningful. One possibility, grounded in string theory, is that our universe is one of many in what is called a multiverse, where different regions of inflating space spontaneously produce different pocket universes with different physical constants. In this picture, what we think of as the constants of nature, things like the speed of light, the strength of gravity, and the masses of particles, could have different values in other pocket universes, and most combinations of those values would produce universes where atoms cannot form and stars cannot shine. We happen to be in one where the constants are compatible with complex structure. This idea is taken seriously by some of the most prominent theoretical physicists in the world and dismissed by others as an unfalsifiable story, partly because if other universes are forever outside our observable horizon, we cannot check. Another possibility is what is called cyclic cosmology, where our universe is not the first or last, but one in an endless series of cycles. In versions developed by Paul Steinhardt and Neil Turok, the universe goes through repeating cycles of expansion and eventual contraction, or the cycles arise from collisions between higher dimensional structures, sometimes called branes. The appeal is that a cyclic model avoids the question of initial conditions entirely, since there is no true beginning, only an ongoing cycle. The challenge, as with the multiverse, is finding predictions that would allow observers to tell this scenario apart from standard inflation. The most quiet and possibly the most honest theoretical position is simply that we do not know what the universe was doing before. The Planck time, which is a duration of about 5.4 times 10 to the minus 44 seconds. Before that moment, the energy densities involved would be so extreme that quantum effects become important for space-time itself, and our two most successful physical theories, general relativity and quantum mechanics, give results that contradict each other when pushed to those conditions. We do not have a working theory of quantum gravity that can describe what happens there. So, the very first sliver of the universe's history is genuinely beyond what our current physics can describe, and everyone working on it knows it. And so, we come to where everything is going, which is, depending on how you choose to look at it, either quite gloomy or deeply peaceful. We are currently in what cosmologists call the stelliferous era, which translates roughly as the era of stars. It began a few 100 million years after the Big Bang and will end somewhere between 10 trillion and 100 trillion years from now, when the last stars finally exhaust their fuel and go dark. We are still in the first few percent of this era. The peak of star formation across the universe actually happened about 10 billion years ago. Since then, the overall rate at which new stars are being born has been slowly and steadily declining. The universe has been gently winding down from its most active period for longer than the Earth has existed. Some near-term predictions by astronomical standards are quite solid. In about 600 million years, the Sun will be bright enough that carbon dioxide levels in Earth's atmosphere will drop too low to support photosynthesis, ending plant life as we know it. Oceans will persist for perhaps another billion years after that. In about 1.1 billion years, rising solar output will push Earth's surface temperature toward conditions where liquid water becomes difficult to maintain. These timescales dwarf all of human history by factors of millions, but they follow directly and unavoidably from how the Sun's luminosity evolves while on the main sequence. Over the next 100 million years or so, the Moon continues drifting about 3.8 centimeters further from Earth every year, because tidal forces between the Earth and Moon are transferring rotational energy away from Earth's spin and into the Moon's orbit. In about 600 million years, total solar eclipses will no longer be possible because the Moon will have drifted far enough away that it will not quite cover the Sun's disk. That striking coincidence, where the Moon and Sun appear nearly identical in size from Earth, is a temporary feature of this precise moment in history. In about 4 to 5 billion years, before the Sun becomes a red giant, the Milky Way and Andromeda galaxies will collide. This is not a maybe. The two galaxies are currently approaching each other at about 110 kilometers per second, and they are close enough that the collision is gravitationally locked in. It will not look like a car crash. It will look like two ghostly structures slowly interpenetrating over hundreds of millions of years, with individual stars rarely actually colliding because the distances between them are so vast. Gravitational forces will reshape both galaxies completely. The merged result will probably settle into a large, diffuse, elliptical galaxy. Our Sun will almost certainly survive, though its orbit will be completely scrambled, and it may end up anywhere in the merged galaxy. The night sky for anyone around to see, it will be unrecognizable. In about 5 billion years, the Sun will exhaust the hydrogen in its core. Without fusion energy pushing outward, the core will contract and heat up, and the outer layers will expand enormously in response. The sun will become a red giant, swelling to perhaps 100 to 200 times its current diameter. Earth's oceans will have boiled away billions of years before this point, simply due to the sun's gradual brightening. But the red giant phase is when the inner solar system faces its final chapter. After the red giant phase, the sun will shed its outer layers as a glowing shell of gas called a planetary nebula, leaving behind its core as a white dwarf. A white dwarf is roughly Earth-sized but contains most of the sun's mass, and it is extremely hot when it first forms. It has no fuel left to burn, so it just radiates its stored heat into space over billions of years, cooling very, very slowly. White dwarfs can sometimes gain a second life. If a white dwarf is in a binary system with another star, it can slowly pull mass off its companion over millions of years. If it accretes enough mass to push past about 1.4 times the mass of the Sun, which is called the Chandrasekhar limit, it becomes unstable and undergoes a thermonuclear explosion that destroys it completely. This is the type Ia supernova mentioned earlier, the standard candle that helped reveal dark energy. The fact that the Chandrasekhar limit is set by quantum mechanics means it is the same everywhere in the universe, which is why all type Ia supernovae peak at the same brightness. After the stellar era, the universe enters the degenerate era, with no new stars forming because the raw material has been used up or locked away in stellar remnants. The galaxy will consist of white dwarfs, neutron stars, and black holes, all slowly cooling or otherwise doing very little. White dwarfs will radiate away their heat for enormous amounts of time. Neutron stars will slow their rotation, their pulsing gradually fading to silence. Brown dwarfs, those objects that collapsed like a star but never got hot enough for hydrogen fusion to ignite, will drift through the darkness, cooling over time scales longer than the current age of the universe. Occasionally, two of these remnants will collide or merge. Two white dwarfs spiraling together can trigger a supernova. A white dwarf and a neutron star merging will produce a burst of radiation and leave behind a black hole. These events will be extraordinarily rare, but given enough time, rare events become inevitable. The degenerate era is expected to last until roughly 10 to the 37th years from now, a number so large that if the current age of the universe were compressed to 1 second, 10 to the 37th years would be longer than the observable universe stretched out in kilometers. According to some extensions of particle physics, protons themselves may be unstable, with a half-life of around 10 to the 34 or 10 to the 36 years. If protons do eventually decay, then all ordinary matter, every rock, every dead star, every cold white dwarf, will simply dissolve away over sufficient time, converting into lighter particles and radiation. By around 10 to the 40 years from now, essentially no ordinary matter will remain in any condensed form. Only black holes will be left, surrounded by a very thin and cold radiation field. Black holes then become the last true objects in the universe. Stephen Hawking showed in the 1970s that black holes are not completely permanent. Near the event horizon of a black hole, quantum mechanics predicts that particle and antiparticle pairs continuously flicker in and out of existence in empty space. When this happens near an event horizon, one particle of the pair can fall in while the other escapes outward. The black hole loses a tiny amount of mass to provide the energy for the escaping particle. Over an incomprehensibly long time, this process, called Hawking radiation, causes the black hole to slowly evaporate. For a stellar mass black hole, evaporation takes about 10 to the 67th years. For a supermassive black hole of 10 billion solar masses, the timescale is around 10 to the 99 years. Eventually, even those last black holes finish evaporating, leaving behind only a very thin and cold gas of photons, electrons, and positrons drifting through an expanding universe. This is the heat death. Not a violent ending, but the calmest possible one. All temperature differences in the universe have fully equalized. All the gradients that drove every process in cosmic history, fusion in stars, chemistry in gas clouds, the movement of planets around suns, have dissolved into a perfectly even, perfectly cold, perfectly dark uniformity. The second law of thermodynamics, which says that entropy always increases in an isolated system, has played out to its absolute limit. There is nothing left to happen. The universe still exists, but nothing can ever occur within it again. The most likely sounding version of this future has been the scientific consensus for several decades. A recent survey called the Dark Energy Spectroscopic Instrument, which mapped millions of galaxies to trace the expansion history of the universe in more detail than ever before, has produced some data suggesting dark energy may be slowly weakening over time rather than staying constant. If that turns out to be true, the timeline or even the ultimate outcome could shift in ways that are not yet understood. It is one of the most watched results in observational cosmology at the moment. There is one more possibility worth thinking about before closing out. Our universe may be in a state called a false vacuum, a configuration of space that appears stable but is not actually at its lowest possible energy level. If that is the case, somewhere in the universe, a tiny bubble of true vacuum could spontaneously form and expand outward at the speed of light, rewriting the laws of physics in everything it passes through. This bubble would be completely undetectable until it arrived, because nothing can travel faster than it. Most physicists think the vacuum is probably stable on timescales much longer than the heat death, but the word probably is doing a lot of work in that sentence, and it is a genuine prediction of quantum field theory. There is also the question of whether the universe is truly infinite in extent. The observable universe, the part we can see, is a sphere about 93 billion light years across, bounded by the distance light has had time to travel since the Big Bang. But the universe itself may be much larger or truly infinite. If it is infinite and roughly uniform in composition, then by pure statistics, every possible arrangement of matter must exist somewhere, including exact copies of every moment happening right now, separated by distances so unimaginably large that the number of digits required to write them would fill entire libraries. This is not mysticism. It follows directly and mathematically from infinite space and a finite number of possible arrangements of a finite number of particles. Serious physicists, including Andre Linde and Max Tegmark, have written about it at length, though others consider it meaningless precisely because it cannot be tested. The universe may be operating on scales so far beyond what we can observe that our intuitions, which were built for estimating distances between trees and the intentions of other people, simply cannot keep up, and that in its own quiet way is maybe the most compelling thing about all of this. Every fact covered in this video, the Big Bang, the cosmic microwave background, stellar nucleosynthesis, dark energy, the eventual heat death, all of it was worked out by creatures who less than 200 years ago did not even know the sun was a star, rather than a uniquely special divine object. The entire modern picture of the universe has been assembled in the blink of a cosmic eye by people using instruments built from materials that were forged in stellar cores and scattered through the galaxy by supernovae billions of years before the Earth even formed. The universe built something that could look back at it and figure out what it was. It did it slowly, patiently, over 13.8 billion years, one collapsing gas cloud at a time, one fusion reaction at a time, one generation of stars enriching the next. And it is still going out there, in the dark and the cold and the enormous quiet, spinning on at its own pace, completely indifferent to whether anything is watching, which, when you are trying to fall asleep, is actually quite comforting. The universe has been here a very long time, and it has a very long way still to go. You can rest